Hello everyone. Now, in the last video, we discovered what we defined as a residue class slash congruence class slash equivalence class, where it's a set of values that are all the same under a certain modular system, all equal to a certain residue. Now let's see if we can develop any special properties to help us discover some, different equivalences more easily. So note that 207 is the same as 25 mod 7. And a good mathematician should not just note that, they should learn why, right? Discover why. And you can discover why with simply dividing 207. Well, 7 goes into 20 twice with a 14, which drops, it gives us 6, drop the 7. That would go in 9 times, which would be 63. And 67 minus 63 is 4, so we have 29 with a remainder of 4. And we would have to confirm it for 25, right? 7 divided with 25. Well, now we go in 3 times with 21, which again gets us that remainder of 4. And since the remainder of 4 is the same in both of them, yes, since the remainders are the same, under division by 7, they are in fact the same values under the modular system. And we kind of did the exploration for the next couple parts. So 207 is congruent to 25 mod 7. 25 is congruent to 4 mod 7. And 207 is congruent to 4 mod 7 as well. Can we generalize this? Is it always true that if A is congruent to B mod 7 and B is congruent to C mod 7, then can we deduce that A must be congruent to C mod 7? This is the transitive property extended to the modular system. And if you can recall from geometry class, maybe, or perhaps even algebra or pre-algebra, the transitive property in like basic arithmetic states that if A is equal to B and B is equal to C, then A is equal to C. That's the transitive property in normal arithmetic. What we're trying to do is demonstrate the modular equivalent of that. Is it also true under the modular arithmetic system and not just the basic arithmetic system? So let's go with some assumptions we can make. I'm going to assume that A is the same as B mod 7. Now, hopefully we've done enough work with the division algorithm to kind of see how this translates into that division algorithm, where what this is saying is that we have that or just go by the definition of the congruence that we originally worked with, that the difference between A and B is equal to a multiple of 7. So 7 times some value k. So once I assume that this is true, I already know that the next part is true. And I am going to assume that B is congruent to C mod 7. Which means that B minus C is equal to 7 times some other integer j. 7 times j. Those are two facts I am working with. The next thing what I want to do with that information is prove that A will be congruent to C. Well, if I let's see. If I take the time, is it going to count it as? All right, whatever. Let's move this over a little bit. There we go. We have two equations. This one here and this one here. And I notice that in one equation we have a negative b, and the other we have a positive. Therefore, if I add those two equations together, they will cancel out the b terms. And like any good mathematician, we're always looking to cancel things out and simplify as much as possible. So I'm going to take our two equations and I'm going to add them together. I'm going to add them together. I'm even going to get rid of these arrows because they might be distracting for now. I think we get the point. So, adding these together, I get A minus B plus B minus C is the same as 7K plus 7J. Interesting. So, what can I do from here? Well, we have negative b plus b. I can rearrange this, use the commutative property. A plus b minus c is equal to, and I'm going to use the distributive property in reverse, factor out a 7, and we have k plus j. And I'll explain why I did that in a second. But now what I can easily determine, alright, b minus b cancels out. These two become a 0 and cancel each other out. So what I am left with is that a minus c is equal to 7 times k plus j. Interesting. This precisely follows that definition, where I can, if I have this, that means I also have that. So what this is saying is that the difference of A and C is equal to 7 times k plus j. We know k and j are integers. K and j are integers. Because it follows precisely from that first definition. I'll even go back to it that we worked with. Where if two integers are congruent modulo m, that is true when their difference is a multiple of m. And that the difference being a multiple of m means that k times m, where k is an integer. Because remember, if k was not an integer, then this whole situation that we worked with in the past wouldn't work. So, if k and j are integers, then k plus j is also an integer. Because if you add two whole numbers together, there's no way of getting a fraction out of that. There's no way of getting a decimal. You must receive another whole number back. So, what this means is that the difference of A and C, is equal to 7 times an integer, which means that the difference of A and C is a multiple of 7. And that firmly establishes the fact that A must be congruent to C under mod 7. And that is precisely what we wanted. We have established the transitive property under modular arithmetic. If A is congruent to B mod 7 and B is congruent to C mod 7, then A is congruent to C mod 7 as well. You've just shown that. So we have this new type of transitive property. And one other way you could have thought about it is that, A is equal to B mod 7. So if we were to set up, one of those columns where it was like 7n plus 1, 7n plus 2, right? And so on and so on and so on. A and B would have to be in one of the same columns. So maybe it was plus 1. A and then B is somewhere on there as well. But B is equal to C. So that means B and C are in the same column, and therefore A and C would also have to be in the same column. That was another way we could have thought about it more theoretically. But I always like the algebraic solutions. I'm a big fan of those. So now this is going to hold true in general. We only proved it for mod 7, but if you wanted to, it's a fairly simple way to extend it to all mod for M, all M. So if A is congruent to B mod M and B is congruent to C mod M, then A is congruent to C mod M as well. The transitive property does hold in modular arithmetic.